Hey, welcome to the ParkerGale YouTube channel. Today we're kicking off a series on the history of computer systems, and this is part one of what we think is going to be a seven-part series. In this first episode, we're going to focus on mainframes and mini computers, which dominated the computing landscape from the early 1970s through at least the middle 80s. Now, while there's a rich history of modern computing before 1970, we're going to start our journey in the middle 70s where the roots of this modern architecture are born. Much of what our systems look like today are derivatives of what we invented for the mainframe and mini computers. Anything prior to 1970 is a little too much legacy. So super interesting to study, but not as important for us in terms of understanding modern computer architectures. So in part one, we're going to cover the golden age of mainframes and mini computers, so 1970 to mid 80s. Following that, we're going to explore the dawn of the personal computer, which is sort of early 80s to early 90s. From there, we'll move into what's commonly known as the client-server era, which spanned the early 90s through the 2000s. And following that, we'll take a look at the emergence of the first version of what we know as the internet, beginning around 1994, and then continuing through 2002, which those of us who were around for that era call the dot-com collapse or the dot-bomb era. And then we'll examine the period from 2002 to 2010, which is the N-tier architecture. So much of what we invented for the internet, the browser, the app server, and the database make up what's known as the N-tier architecture, which is the successor to client server. And then 2008 to 2018 saw the rise of mobile applications where, offering a mobile version of your desktop or browser applications became a core part of the technology ecosystem. And then finally, we'll delve into the era of cloud computing as hosting applications in AWS or Azure or Google Cloud took over from either building your own data center or working with a third party like Rackspace, where they would simply just hosting your equipment. Now, it's important to note that these eras didn't have really hard and strong and fast transitions with clear-cut boundaries. They overlapped, blended into one another as technology from each phase matured. So that's why you see in our agenda here, a lot of the dates overlap because the technologies overlapped as well. So there wasn't clear dates and times where one era moved into the next, but sort of a blending of these architectures. So part one, let's just talk quickly about the agenda for today's presentation. We're going to start by talking about mainframes and mini computers, what set them apart, how they coexisted, and how they laid the foundation for the software ecosystem we rely on today. Now, it might sound like ancient history, but trust me, a lot of the architectures and the things that we did in those days still applies today. It still matters. We'll spend a minute talking about each of the four building blocks of a computer at a very high level: the CPU, memory, disk, and networking. But we're not going to spend a lot of time on networking in this particular presentation. It'll become much more important in future parts of this overall conversation. Next up, I'm going to indulge in a bit of a personal side trip and spend a moment talking about Y2K. Yes, the infamous year 2000 problem. If you lived through that era, you'll remember the buzz. If you didn't, it's a fascinating look at how deeply we came to rely on systems design using some very short-term assumptions. We'll also cover the primary way that users interacted with computers back then. Today, it's all about browsers, mobile apps, PCs, chat GPT agents. But at one time, it was terminals or nothing. We'll explore what that meant and how it shaped systems design on a go-forward basis. We're not going to spend too much time on networking. We'll talk about it in terms of the four building blocks of a computer system, but we'll talk more about networking as we get to the middle 80s and 90s when it became much more important. We'll take a look at databases and file systems from that era. So what people used to store data, how these systems worked, and which of these databases or platforms are still hanging around today. We'll also talk about popular programming languages of the time, again, some of which are very much alive and kicking, to steal a phrase from Simple Minds. And last but not least, we'll talk a little bit about the dawn of application software, the early days of buying complete software packages instead of writing your own software in-house. This marked the era or the rise of what's called the ISVs, or independent software vendors, and it was a real turning point in the growth of the industry and happened right around this time frame. And then finally, we'll set the stage for the next part of this discussion. We'll wrap up with a snapshot of where we stood circa 1985. So we'll start this conversation today in the early 70s, take a ride through the foundational era of computing, and then part one just before the rise of the PC, which we'll pick up again in the next episode. So let's start with the big question. Why do we even care about the history of computer architectures, at least for the purposes of investors, which we are in private equity buying software companies? Well, for us, the answer is pretty simple. Modern computer architectures are direct descendants of the mainframe and the mini computer era, and a lot of techniques that people use to develop large scale systems and mainframes and minis are still relevant today. A lot of the same techniques that you use, approaches that you use to solving problems, while they use different operating systems, different hardware components, a lot of the approaches were the same. So studying the past here gives us a guide map for the future. And to borrow a quote from, as is often done, from George Santayana's Life of Reason, those who cannot remember the past are condemned to repeat it. So, looking at the older computer architectures both allows us to understand what we built today and how modern computer systems work, but also understanding the mistakes and trying to avoid those mistakes on a go-forward basis. And this absolutely applies to the world of computing. You'll notice many of the architectural patterns and design choices that we talk about, both in hardware and software, have been used, reused, recycled again and again. In fact, there's a school of thought that says the entire computer industry just oscillates between centralizing things and decentralizing things. And you'll see that throughout the conversation across these 7 different parts as we move forward. So a lot of what we're going to cover here isn't just historical trivia. It actually still applies to the architectures that we're using today. And if you work with large scale enterprise systems, chances are pretty good you'll be asked to integrate with architectures that are dating back from the 70s. So you may be required to integrate into certainly a mainframe or an IBM branded mini computer, but you may also still have to talk to a Sun Solaris box or VAX VMS system in some cases. Another major theme we'll touch on here is how much of the engineering effort back then in the 70s and 80s was focused on resource constraints. CPU, memory, and storage were precious commodities. Software developers in the 70s and 80s had to be extremely clever about how they wrote code. They were constantly optimizing for performance to squeeze every ounce of efficiency out of these limited systems. Hardware was expensive, and you had to make the most of it. The interesting thing is, here's the kicker. We're starting to see this mindset return, especially in the age of AI. AI consumes so much resources in terms of memory, CPU power, processing power, that many of the techniques that we use are things we used to focus on to improve performance or focus on resource utilization is coming back to the forefront again as we start to build some of these very, very large scale systems with AI. Why is that? Because AI workloads are intensely demanding. Just like older large-scale systems with limited hardware resources way back in the 70s. So we're back to talking about CPU, memory, and disk, not just in the abstract, but in real operational terms. Optimizing software for performance and resource usage is becoming relevant again, just like it was decades ago. Ergo, the rise of NVIDIA. And finally, let's not forget, there are still plenty of mainframes out there, and to a lesser degree, mini computers running today. You might come across them in a portfolio company during M&A due diligence or in a customer's legacy stack. Understanding how these systems were built and why they behave the way they do is essential if you want to integrate or modernize these systems on a go-forward basis. So, first things first, let's talk about the differences between a mainframe and a mini computer. And I'm going to keep this really, really simple, focusing on just a few key categories. Let's start with scalability. Mainframes were built to handle vastly more concurrent users and processors than mini computers. Now, I'd put a little asterisk. Are they really concurrent? Not really, but for the purposes of this conversation, it feels that way. These machines were bigger, they were more expensive, they could run larger, more complex programs. Their hardware and operating systems were far more sophisticated, especially in terms of resource management, and things like CPU scheduling, memory management, and I/O optimization were, leagues above what you might find with some of the smaller mini computer vendors. Why was this the case? Well, because mainframes often had to juggle thousands of tasks at once. Again, they weren't really processing them at once, but the appearance of handling lots of tasks, starting them up and stopping them, switching between tasks, mainframes handle very, very large numbers of those. On a comparative basis, while a mainframe might handle thousands of tasks, a mini computer might be handling hundreds of tasks. Now, these are not low-level system tasks, but think of it as business logic tasks. While not everything was truly parallel in these operating systems, many things were swapped in and out of memory. It often felt like mainframes were doing lots of things at the same time. Another key difference for mainframes over mini computers is reliability. Mainframes came with built-in fault tolerance, automatic recovery, and layers of redundancy that were baked right into the hardware and the operating system. And that level of dependability didn't come cheap, but for industries like banking or airline reservations, where uptime is critical, this was a must-have. With a mainframe, you didn't have to code all that reliability into your applications. The operating system and the hardware itself handled it for you, but you paid a price to do it. Mainframes also tended to feature a much stronger security architecture. They offered more fine-grained granular controls, user isolation, and a more comprehensive model than what you'd find in most mini computers. Um, Unix systems are just smaller boxes. Again, this was necessary because these systems often hosted dozens of departments and thousands of users, all running essentially simultaneously, whereas it was a much smaller number of users and often a departmental solution when you talked about a mini computer. The operating systems on these high-end machines were highly optimized for throughput and efficiency and at a truly massive scale. And this is why mainframes became the go-to systems for banks, credit card processors, insurance companies, basically anyone who needed to crunch enormous volumes of data reliably and quickly. Now, to be fair, some of the earliest IBM machines that were labeled as mainframes wouldn't seem all that powerful by today's standards, but by the time we got to systems like the IBM System 360 and System 390, these machines were true enterprise workhorses designed for maximum throughput, rock solid reliability, and lots of scalability. And to repeat myself, all of that came with a cost. Mainframes were expensive, not just the machines themselves, but the environments that were needed to run them. You don't really see the classic computer room or data center room at a company anymore. But if you've ever seen photos of modern AI data centers or AWS's or Azure's data centers, the vibe is pretty similar. These systems needed special power, industrial scale air conditioning, and in many cases, even water cooling for some of these larger mainframes. You'd find raised floors, custom wiring, and serious infrastructure to support them. So not only were the machines more expensive, but the environment needed to run those machines or maintain those machines was also much more expensive. So if we pick things up around 1970, give or take a few years, depending on the specific technology or trend we're talking about, but for our purposes, 1970 is close enough. In the mainframe world, this era was all about IBM and the seven dwarfs. So IBM dominated the mainframe market. They were the giant, no question. But there were other players in what was considered the mainframe game, and they were collectively known somewhat affectionately as the seven dwarfs. And that list included Burroughs, Univac, NCR, Control Data, Honeywell, RCA, and General Electric. Some of these are names that are still around that have been merged into other companies. Some get out of the computer hardware business altogether over the years. But IBM was the dominant player on the mainframe side. But there were still plenty of guys nipping at the heels, but not close. On the mini computer side, the market was even more crowded. By the late 1970s, a few companies had clearly pulled ahead. DEC was the clear number two, really popular in manufacturing systems, smaller data centers. They were kind of the mini computer of choice, particularly the DEC's VAX line, which was their most popular line of computers. Hewlett-Packard had a big presence with their HP 3000 machines running the MPE operating system. Out of Boston, Wang Laboratories was really a market leader in office automation and immensely popular in the late 1970s. Data General, which was a spinoff of some guys from DEC, produced some very popular 32-bit operating systems back in the 70s. But DEC was kind of the leader of that crew. Now, at the tail end of the 70s, certainly got much more popular by the middle to late 80s. But there was a third category that began to appear. Those would be hardware vendors running Unix operating systems. Now, Bell Labs from AT&T built the original version of the Unix operating system. It was developed in the late 1960s and early 70s by Ken Thompson and Dennis Ritchie and their team. These are the same guys who built the C language, just for interest's sake. This earlier version of Unix, which was often called Research Unix, was cutting edge. It was a minimalist operating system designed for flexibility and portability. It was a research tool, not a commercial product, but it laid the foundation for what would come later. If we fast forward to the early 1980s, AT&T decided to commercialize this operating system, and that's where they they named System 5. System 5 Unix comes in, was released in 83 and represented a formal productized version of Unix intended for commercial use. They licensed that operating system. So while Bell Labs Unix was the original version, System 5 was a branch, a cleaned up, feature-rich version designed for licensing and deployment to hardware vendors. And it was adopted by a lot of vendors. IBM had their AIX operating system on their RISC 2000, RISC 6000 hardware architecture. That was based on AT&T System 5. HP had HPUX, Sun Microsystems, before ultimately switching to BSD, the Berkeley variation of Unix. They started out with System 5. And while the legacy vendors such as IBM, DEC, and HP all produced Unix mini computers, the market began to get filled with Unix first vendors, folks that built their hardware and only had some variant of the Unix operating system running on their platforms. Vendors such as Sun Microsystems, Secret Computer, and Pyramid fall into this category. These were the major players shaping the mini computer era, and they helped pave the way toward the computing models we rely on today. Mainframes were built for enterprise critical applications. Think banks, insurance companies, credit card networks, airline reservation systems, anything where high volume transactions, uptime, and reliability were absolutely mission critical. Mini computers, on the other hand, were typically used for departmental computing. Smaller groups of users, smaller applications, and generally more constrained environments, although they could often live in an office building where there wasn't a commercial data center. This is not true for the early versions, but by the early to middle 80s, when DEC came out with the microvacs, that thing could actually just sit really in a closet in your office. Now, to paint a simple mental picture, and yes, I've made this overly simple just to show you the concept. The classic mainframe setup or mini computer setup looked just like this: a terminal connected via physical cable to a mainframe. That's it. Just a keyboard and screen linked directly to the computing platform. Now, I've got an asterisk here because it wasn't quite this simple, but initially it really was. You literally had a cable that ran from your terminal to the back of a board on your mainframe or mini computer, and that's how the terminal connected to the machine. So it wasn't always this simple, but just for the moment, in the earliest days, this is exactly how it worked. If you wanted to interact with the mainframe of the mini, you had to be physically connected to it, often over serial or coaxial cable. Now, we're going to talk more about terminals in a bit, but because it's a whole topic on its own, I'll hold off on some of the details here. But here's the important thing to note for the moment. In this architecture, whether you're using a mainframe or a mini computer, all the work happened on the central machine. That includes the code that was running, the data, the business logic, everything. The terminal you were using wasn't running anything locally. It was basically a typewriter with a screen, a keyboard to send keystrokes, and a monitor to display results. That was it. No local processing, no storage, no applications running on the terminal itself. Now, I'll drop in another asterisk here for the IBM 3270 terminal, which is a bit of a special case. It had some features that set it apart, and we'll cover that when we get into the terminal section of this conversation. Now, let's zoom out a bit. I'm going to take you from just one terminal talking to a mainframe to what a typical environment might have looked like. So if we zoom out into a real world production grade, corporate mainframe deployment look like, especially for large companies, it looked like something like this. At scale, a large enterprise might have more than one mainframe, but for simplicity's sake, let's assume they had just one. And here's typically how it laid out. In the main office, in a specially designed computer room, you'd have your mainframe. That big, powerful box that we've been talking about connected to a bunch of terminals. But I'll introduce a new concept here, which you can see in the square to the upper left corner: terminal controller or terminal server. As organizations scaled up, terminals didn't always connect directly to the mainframe anymore. In fact, they were often connected to a terminal controller or a terminal server, which routed the communications to the mainframe. And it acted as a bit of a one-to-many. You could have a n number of terminals talking to a single terminal controller that had an individual connection back to the mainframe. So it allowed you to get far more numbers of users and terminals connected to that mainframe than would have been supported by just a cable that for each terminal that plugged into the back of it. It also allowed you to distribute the terminals further away from the actual computer. In many cases, you'd have one physical location with a whole bunch of terminals and a whole bunch of terminal controllers, which in turn talk to the mainframe. This made it easier to manage the growing number of terminals without overwhelming the mainframe's input lines. But it didn't stop there. On the right-hand side, we've got a couple of remote offices, and these would be satellite locations that needed access to the same mainframe. These offices would have their own local terminal controllers, and those would connect back to the mainframe in the main office over the public switch telephone network, which most of us think of as traditional phone lines or copper wire, because at this point, almost all that network was 100% owned by AT&T, especially before the early 80s when AT&T was broken up by the government. It was all owned by AT&T. So these kind of network setups were expensive and complicated. It required a lot of coordination with the telecom carriers to make it all work. You had to get the lines provisioned, deal with reliability issues, maintain a bunch of different network protocols, many of which we're not going to get into here today, will become more important when we talk about the internet era, but for the moment was not that relevant to kind of the architecture we talked about. So I've drawn this complicated public telephone network as just a simple cloud. It wasn't really a cloud, just to simplify things visually. But what's important to know is this: if the company was big enough to own a mainframe, it was also certainly big enough to have multiple offices, each with their own terminals, and terminal controls, and printers, more than likely, all connected through, quote unquote, cloud of telephone network infrastructure back to the central computer center. So while the technology may have been very different from today's internet-based infrastructure, the concept of centralized computing with distributed access has been around for decades, since the mainframe. It's also worth noting that in a lot of large companies, mainframes and mini computers often coexisted, living together in what we might call one big happy family, although they weren't always happy. To be clear, they were generally not connected to each other. So your IBM mainframe might not be connected to your DEC VAX by intention. If you're looking at this slide I'm referencing, you'll notice I've drawn it that way on purpose. The two satellite offices are connecting back through the public switch telephone network to the mainframe, but my mini computer is sitting off in its manufacturing facility, not talking to anybody else. So if you had a manufacturing facility or multiple facilities or a remote branch office, instead of connecting to the corporate mainframe, those locations might be running their own mini computer system locally. And this is a very common deployment model. So you might actually have your IBM mainframe living at headquarters, handling financials, HR systems, or any other kind of enterprise-wide system, billing, invoicing, whatever. While your manufacturing plant might be running just your materials resource planning process or your ERP processes on a DEC VAX or HP 3000 machine. So the key point here is in many cases, these disparate systems, the mainframe and the mini computer, they weren't connected at all. You could technically pipe data from the mini computer to the mainframe, but more often than not, that did not happen automatically. What happened instead? You might actually print out a report from the mini computer, and then somebody back at head office might rekey that information into the mainframe. Literally. So maybe your ERP system, the one controlling your plant floor and local inventory and production, could be running entirely on a DEC VAX. And when it came time to do invoicing or accounting, someone might literally sit down and retype invoice records into the mainframe. And this setup wasn't unusual. In fact, you see this all the time in big corporations from the 70s and 80s. One or more mainframes at the center and a fleet of mini computers often deployed at remote sites. Sometimes the mini computers lived on-prem at those satellite locations, but they could also sit right in the same corporate data center. So there was no technical limitation there. Users of the remote facilities might have been accessing them over DEC terminals and terminal controllers, just like the mainframe uses, and just like they worked in the mainframe. But, and again, I'll stress this, the mainframe and the mini computer were often not connected, even if they were in the same data center. They ran parallel systems serving different parts of the business, oftentimes with manual handoffs between the two systems. So let's take a very simplified view of the four major components of a mainframe or mini computer. And we'll boil it down to what we'll call the four fundamental building blocks. So first up on our list is the CPU, aka the central processing unit. This is the brain of the computer. For many years, performance was measured in something called MIPS, or millions of instructions per second. Now, MIPS isn't widely used anymore as a way to measure the processing power of a CPU, but it's still a helpful yardstick when you're comparing machines across different eras. It's what we might call close enough for government work. At its core, the CPU determines how fast a machine can process instructions, how many tasks it can juggle, how quickly it can swap between them. And then back in the day, most computers handle just one process at a time. Parallel processing wasn't really a thing yet. And again, put an asterisk on it. There was some early indicators. But if it was limited to things that might assist the CPU, like floating point processor boards, et cetera. Compared to today, where we have machines that have multiple CPUs, multiple chips in every machine, oftentimes handling tasks in parallel, and suddenly the landscape looks very, very different. But at this point, think of it as one CPU per machine. Next up is memory. Random access memory, which you often hear to refer to as RAM. Back in the early days, memory was measured in megabytes, i.e. millions of bytes. Now, of course, it's all about gigabytes and beyond. Memory is the system's short-term storage. It's fast, but non-permanent. You shut the machine down, memory goes away. Again, little asterisk here. Oftentimes, mainframe systems had some very advanced ways to keep memory from actually being powered down in the event of a system failure. And you could restore the system to exactly the same state. Again, one of the reasons you paid for a mainframe. For our purposes, think of it as fast but non-permanent. In a couple of minutes, we'll briefly talk about concepts like swapping and paging, which allow us to get a lot more out of memory. And they were vital in terms of getting larger scale systems to run on things like mainframes and minis. But they're not top of mind for most developers today. So we'll just touch on it for just a minute. The third pillar is disk storage. And this is your permanent, non-volatile storage. This is where data stays even when you shut down the machine. It's your library, it's your storage, it's your vault. In the early days, storage was measured in megabytes, then gigabytes, and now we're regularly dealing with terabytes, even petabytes in some cases, especially in large-scale enterprises or AI-driven environments. We'll take a look at a few slides here at the maximum disk size, how many drives you could attach to a machine, because it was much more limited than it is today, and how storage costs have really plummeted over time. Though we still care about the cost of storage and how it's deployed when we're building large-scale systems. Now, I've grayed out network here because we're not going to talk too much about networking. It becomes much more important in later parts of this presentation, but pretty primitive in terms of having to worry about it at this level, right? So the network was a way to connect terminals to the machine, potentially machines to connect to each other, but they really didn't because they spoke different languages, if you will, at that point. But I've graded out for today's episode because networking really wasn't a major factor in the 1970s or early 80s. Most machines operated in isolation without a standardized way to communicate with each other. Now, we'll be talking a lot more about it in future episodes because it does become much more of a key part of central system design, but it wasn't as important in terms of machine-to-machine communication or architecture in the 70s and 80s. Now, before we dive into comparisons of CPU and disk across eras, I want to take a minute to explain a very important concept from the early days of computing: swapping versus paging. Originally, when you wrote a software program, the entire program had to fit into memory, no exceptions. So if your mainframe or mini computer had 1 megabyte of memory, your compiled program needed to be smaller than that. In reality, it probably had to be much smaller because the operating system itself needed some of that space too. But for simplicity's sake, let's assume the full megabyte was available to you. The point is, developers spent a lot of time optimizing their code just to make sure it could fit into the memory constraints of the machine. This wasn't something that was optional. It was the only way to get software to run. And memory was also expensive. Now enter the concept of swapping. Swapping was the operating system solution to let multiple users or programs share a single machine. So here's how it worked. When the CPU was finished processing one user's program or a slice of that user's program, the system would swap that program entirely out of memory. Take the whole thing out, stick it on disk someplace, a reserved portion of disk that the CPU knew how to work with and pull back. It would temporarily store it there, and then it would swap in another user's program and data, loading it into memory so the CPU could process that next. This allowed your mainframe and mini computer to give the illusion that it was running hundreds of programs at the same time, but it really wasn't. Essentially, the machine was running one job at a time, or rather a piece of a job, swapping the code in and out of memory for each user or process. This process repeated in sort of a round-robin fashion. It worked, but it came with a high overhead. You were moving an entire program in and out of memory each time you swapped. This created a lot of I/O, input-output, and it wasn't particularly efficient. To address this, software developers designed a more elegant solution, which is really how machines work today: paging. Paging took a finer grained approach. Instead of moving whole programs out of memory, the system would move individual pages of memory. So as more memory became available, they could keep parts of users' programs in memory, but they could also allow a program that was too big to fit in memory to pull pages of memory in, right? So typically a page of memory is about 4 kilobytes because machine stock base 2, 4096, with about 4,000 bytes available to you, 96 available to the operating system for managing that page, essentially. This was much more efficient and allowed for lower overhead. The trade-off was it was more complex to implement in the operating system, but that complexity paid off in scalability because you were no longer limited to the physical memory of the machine in order to the size of program that you wanted to run. So through the 60s to the early 80s, most major operating systems, including IBM's DEC, early Unix systems, used a combination of both swapping and paging. Most of them used swapping initially, but paging eventually became dominant as the systems matured. By the 90s, with operating systems like Windows NT, early versions of Linux, Solaris, IBM's AS400, paging had clearly taken over. And by the 2000s, virtually every major operating system had, pun intended, swapped out swapping in favor of paging. Why it's important is that this shift from coarse-grained swapping to fine-grained paging was a fundamental architectural change. It allowed us to dramatically scale the number of users and programs that could run on a single machine, and it allowed us to run code that was larger than the amount of physical memory available. Without paging, we wouldn't be where we are today. So now that we've talked about CPU, disk, and memory, let's just do a quick comparison from some machines of the late 70s era to machines you might know of today. So if we look at a quick comparison across time, we can see how far we've come in terms of 3 of the 4 key building blocks: CPU, memory, and disk. Again, we're leaving networking out of this for now, but just to keep this thing focused, but we will talk about networking when we get to the internet. So if we go back to the 1970s with IBM's 3090, which was a top-of-the-line mainframe in those days, its CPU clocked in at between 20 and 30 MIPS, or millions of instructions per second, which was pretty powerful back then. For memory, those machines could have 512 megabytes, which was huge for the time, but by today's standards, not all that impressive. And disk storage, each disk drive held about 300 megabytes. You could attach potentially a lot of drives to your machine, but the concept of things like a single file spanning multiple disks really wasn't well supported yet. Engineers had to be clever about file sizes because everything mostly needed to fit on a single disk. In fact, disks were really in 2 pieces. You had the container that actually ran the disk, and you had the physical platters from the disk yourself that you would literally punch into this controller, shut the top, turn on the vacuum control, spin it up, and that disk was available and mounted to your operating system. So you often had a smaller number of physical controllers, but you might have lots of disks that were taken offline and stored in cabinets. So people did a lot of moving disks around. Prior to that, it was all tape and punch cards, but at this point, you might have multiple removable disks, and you would basically change out the disk. Your system operators would change out the disk when you needed to deal with a certain amount of certain data that was on one disk or another. Now, if we fast forward to not just the leading edge, but even a couple of years ago, an IBM Z15 series mainframe, circa 2019, this machine could hit 1.2 million MIPS. So just look at the comparison between the original 3090 and a machine from our common era, literally 1.2 million MIPS versus 20 or 30. That's not a typo. Pretty amazing. Memory, most mainframes these days have anywhere from between 16 to 64 terabytes. Yes, that's terabytes. We used to talk about megabytes like they were gold. Now we're comfortably living in terabyte territory. And storage, it's all over the place. But you can easily find 15 terabyte drives and high performance disk drives. Storage isn't unlimited, but we're close enough for most use cases today. Nobody is taking disks offline or online anymore. There's no removable packs. Like, disks are much faster, much higher capacities, and they transfer data much, much quicker than they did in the old days. Now, if we jump over to the mini computer world, a DEC VAX 11780, that's the first VAX I ever worked on, was an 11780. The first machine I ever touched was a DEC PDP 1123 running the Ristus operating system, but VAX 780 was the first VAX machine I ever worked with. That machine ran around 1 MIPS. So what, 1/20th, 1/30th the size of power of a mainframe. Memory maxed out at about 128 megabytes, and disk drives typically held 175 to 300 megabytes, depending on the model. And the memory and disk were super expensive, not cheap. 1980s dollars, they varied anywhere from $100 per megabyte to up to $300 or $400 per megabyte of disk space. Now, just for perspective, if we look at an Intel 286, which is an early PC processor that came out in the 80s from Intel, it delivered the same MIPS as a VAX, believe it or not. That desktop CPU produced about 1 to 2 MIPS when a VAX 780, which was considered state of the art in the early 1980s, you delivered about the same MIPS. Pretty amazing. The difference was memory. Memory was very limited on those PCs. Most PC systems initially had between 256 kilobytes and maybe 4 megabytes, but that was considered a theoretical maximum and pretty expensive. And for the most part, the only thing that was addressable with the operating systems that ran on those PCs were the 640 kilobytes that were considered main memory. You had to jump through hoops to use any of the memory above that. So it was simply a way to get a data space, and it was a lot of complicated programming. You were kind of getting down to the guts really to make use of it. Storage on those early PCs, most of them just had floppy disks, but a 20 megabyte hard drive was massively expensive and not that large. For comparison purposes, this presentation, which doesn't have a lot of graphics in it, still chalks in at about 10 megabytes. So, a PC disk could store, two copies of this presentation, and a DEC VAX or a mainframe might only be able to store 10 copies of it comfortably. That's how limited the storage was. Now, if you fast forward to a modern Intel-based x86 server, they routinely run 800,000 MIPS. They can often take up to 12 terabytes of memory, and multi-terabyte, 32 terabyte hard spinning drives, and super fast SSDs with no moving part drives. Very common plugged into those servers. So storage performance has radically increased, and storage costs have radically dropped since the 70s and 80s. And here's the ultimate kicker: your iPhone 15 Pro. Yep, the one in your pocket, runs at around 180,000 MIPS, believe it or not, from a comparative standpoint. Most of them support 6 to 8 gigabytes of memory, and you can support up to a terabyte of storage. So just let that sink in. I know you've heard this, but you've seen it live in terms of the numbers. Your smartphone is dramatically more powerful than the biggest and most expensive computers from the 70s and 80s. Mainframes that used to require raised floors, water cooling, and a team of specialists to operate, back then are outclassed by the device you use to text your friends and play Wordle. Pretty amazing. Now, before we go any further, I'm going to take a quick detour and talk about one of the big infamous moments in modern computing, or Y2K, so-called the Millennium Bug. Now, you've probably heard the story. In the late 1990s, the tech world went into full-blown panic mode over what would happen when the calendar flipped from 1999 to 2000. And while it might sound like hype in retrospect, the concern was very real because of the limitations of storage and memory that developers faced in the 70s and 80s. So let me explain. Back then, computers, software developers often stored dates in a more compact format. Instead of 8 characters, they would use just 6 characters. So, for example, a date like March 25th, 1955 might have been stored as 550325. 2 digits for the year, 2 digits for the month, 2 digits for the day. Why? Because storage, as we saw on the previous slide, was expensive, really expensive. So let's break it down. We're going to take a fake example from the insurance industry. I happen to pick insurance because it's got a lot of dates. So if you were storing just a single record, and the single record just had a date field at 6 characters per date, 8 bits per character, that adds up to basically 48 bytes of storage for that one date field. Now imagine those same developers decided to future-proof their system and use a 4-digit year instead of 2 digits. So 1955 instead of just 55. That means you're now storing 8 characters instead of 6. And by the math, that's 64 megabytes. So 16 extra bytes just for those 2 fields. Makes sense, of course. 8-bit bytes, 8 bytes to the character. So 16 extra bytes in order to store those 2 extra century values. So in this case, it's just 16 bytes for that one date. And we're only talking about one date for one record. So it doesn't seem like a lot. But if you think about insurance records, for example, might contain dozens of date fields. And I've listed some of the examples here below: an effective date of policy, end date of the policy. You might need the birth date of the person that's got the policy. When is the bill date? What was the cancellation date? So you can see there'd be a proliferation of dates that you might need just for a simple insurance record. As you look at the number of date fields you might need and the number of records you might store, the numbers start adding up pretty quick. So consider this. In the 70s, this storage cost about 100 bytes per megabyte. And I'm being kind here. I kind of average this out because a high-end IBM 3380 disk in 1980 priced out at about $32 a megabyte. But some of the disks on the mid-range systems were much more expensive. They ran closer to 200 or 300 per megabyte. And that didn't include all the power costs, all the extra controllers, just the disk itself. So if we assume that our little insurance company had 20 date fields across 250,000 records, you're looking at $24,000 in storage costs just for the date field alone, not the rest of the record. I'm just simplifying this just to the date itself. 20 date fields. We still didn't capture address. We didn't capture name. Just the 20 date fields we might use for insurance. If we had 250,000 records, that's $24,000 worth of storage costs. Now, if those same developers and decided to future-proof their system and use a 4-digit year instead of 2 digits. So again, 1955 instead of 55. That means you're now storing 8 characters instead of 6. So the math, that's 320 megabytes total. So 64 bytes times 20 date fields times 250,000 records, or 320,000 megabytes of storage at $100 per megabyte. That would be $32,000 in 1970-ish exchange rates. That's an $8,000 difference just for that one record type alone. And in today's dollars, that'd be closer to $32,000. So that's a big cost when you look at your average software developer was making in the 20s. That $8,000 difference could be more than made up for by a software developer, right? So because storage was so expensive and memory was so expensive too, remember these dates had to fit in memory. So what did developers do? They stuck with 2-digit years because at the time for business systems, it made perfect sense. Most of these systems were built in the 70s and 80s. They weren't really dealing with data that was living in the past. So anything looked like a go forward date as opposed to a historical date. And to be fair, the year 2000 seemed like really, really far away. Most developers assumed they could fix it later or just use business logic to infer the correct century. So, if it looked like the number for year looked like something that might be in the past, they could assume, no, they meant the future version of that. So if they saw 01, they might not think of 1901, but they might think of 2001. Adding this logic to every program didn't scale very well, and that's why the industry had to scramble in the late 90s to patch, retrofit, and test countless legacy systems before the ball dropped on New Year's Eve. And it was a massive effort. It cost a ton of money. It's probably worth its own episode, but just as an aside, it's important. I think as you see here, resources were so expensive, you can see why people were trying to use the shortest dates or the shortest expressions of text they could possibly do when they stored a value. At the time, saving a few bytes per record wasn't just optimization. It was a business necessity given the cost. So yes, Y2K was real. It was a direct result of the resource constraints from those early decades of computing, as opposed to just a bunch of us software developers zoning and not thinking it through. There was a real cost to storing those extra 2 characters. That's why we did what we did. So we spent some time talking about the size of machines, storage capacity, the difference between mini computers and mainframes. We're going to shift gears for a minute and talk about something more tangible, literally how everyday users interacted with these machines. And the answer was terminals. So users interacted with the mainframe or mini computer via terminal, what we now consider a dumb terminal. These were essentially keyboards with screens, and they served as the main interface between the user and your mainframe or mini computer. You'll hear these terminals referred to as CRT terminals, short for cathode ray tube, which was the display technology used at the time. These were old school tube-powered monitors, long before the concept of LCDs and flat panels were even a twinkle in somebody's eye. So that's the reason they're awful big, because they still had a tube behind them. So let's just meet a few of the popular terminals from that area. First, I'm going to talk about the DEC VT100. This is actually the first CRT terminal I ever worked on. It was extremely common in many computer environments and had a huge footprint across labs and tech departments. It was a real workhorse. Next to it, you see Sun Microsystems, Sun One Workstation. Um, you'll find by the 90s they were known for their servers and graphical displays, but their Sun workstations, their initial Sun workstations, were extremely influential, especially as we started the 90s. And again, we'll dive more into workstations in future episodes, but they were really the power users terminal of choice for that era for Unix boxes. Down the lower left, you got the vaunted Lear-Siegler. So Lear-Siegler was not necessarily a computer manufacturer, but they made terminals that worked with lots of different vendors, mini computers and mainframes. They were supported by a wide range of hardware vendors. They were fairly universal in the mini computer era. Companies often use them as a point of sale terminal. So you would literally see them in stores instead of a cash register, believe it or not. And then in the middle, you see the legendary IBM 3270. Now, I'm not a big fan of the word game changer, but in this case, it does fit. The 3270 revolutionized how users interacted with mainframe systems, and we'll go into more detail on that in the next slide for a feature that was added to the 3270. Now, last but not least on this page, before CRTs came along, around the time I first got my hands on computers, many terminals didn't even have screens. They used paper-based terminals like teletype machines. You typed in your commands, they printed out on a folding paper that loaded from the bottom of the machine, and the responsive computer printed out just like on the same folding paper like a typewriter, just like the deck writer pictured here. So that was literally the first machine I ever touched was a deck writer. And we had very few DEC VT100s available to students. So you would scramble to get that VT100 if you could. What you'll notice is no graphical user interface, no windows, no mouse, just a command line and a continuous stream of paper. So if you were using a mainframe or mini computer back in the 70s or early 80s, odds are you were either staring at a green and black screen CRT or watching commands print out in real time on folded paper. So we mentioned the 3270, and it's important to revisit it here again. There's something that might look small on the surface, but actually had a big impact on how users interacted with computers and software back in the day. And that's the difference between character mode terminals and block mode terminals. Now, these two modes define how terminals communicated user input to the mainframe or mini computer, and they're fundamentally different. Character mode terminals, which we can call character at a time, in a character mode terminal, every single keystroke you sent is immediately echoed to your monitor and sent to the host system. So the most well-known example from the previous slide would be our DEC VT100 or earlier teletype machines, what we call TTYs. Even modern terminal emulators often behave this way. So you hit a key, go straight to the host. The system responds in real time or near real time, echoing back the characters and then validating the input almost instantly. The terminal itself did very little. It's just passing characters along. All the real processing happened on the host. For the most part, yes, the terminal still did something, but all the core processing that got done was being done on the mini computer or mainframe, and the data was sending back to you at the terminal. The benefit of this was simple. You get immediate feedback, perfect for command lines environments or interactive shells. The downside, because every keystroke triggered a network transmission, it generates a lot of traffic. And that puts more strain on the host system. And if you're dealing with a high latency connection, the user experience can really suffer. If you were connected to your mini computer with what was known as an acoustic coupler, literally you used your telephone and you plugged into a little plunger and dialed up your host computer system, and it worked at 300 baud. So very, very small number of characters per second. Working in a keystroke by keystroke fashion could seem painfully slow. Enter block mode terminals. One of the first block mode terminals was or maybe the first, was the IBM 3270 that we mentioned earlier. In this model, you can think of the terminal as more like a form, more like a screen. The user filled in entire screens of information, tabbing from field to field or position to position on the screen. And only when they're done would they hit a transmit or a PF key and send the whole block of data to the host at once. Input was buffered locally by the terminal until the user pressed the submission key. Terminals were able to enforce a limited set of field level rules, so they could make certain fields on your screen read only, make sure it's a number, not a character, and even hide fields as necessary. So more local processing was available, which meant fewer round trips to the host. The upside, much more efficient, especially in environments with limited bandwidth or high latency. It was ideal for form-based applications, what made it perfect for mainframe and so-called green screen systems. Now, the trade-off, you don't get real-time feedback. Nothing is processed until that full screen is submitted. And because the terminal has to do more on its own, it needs to be a bit smarter under the hood. And so did the terminal server. So summarizing the difference, character mode sends input one keystroke at a time, great for command line use. Block mode waits until the full screen is completed and then transmits it in one go. Perfect for structured form-based applications. So on this particular screen, I've given you a selection of block mode terminals and character mode terminals on the right. Every hardware manufacturer made a series of terminals, and there were lots of third parties like Lear Siegler that made terminals that supported multiple brands of mainframes and mini computers. So there were a proliferation of terminals back in the 60s and 70s, all the way through the 80s for sure. Now let's just shift gears for a minute. We're going to move above the hardware just a little bit to the software that got layered on these machines. So first up, we're going to talk about databases and file systems, how we stored data, how we accessed and stored data that was living on the mini computer or the mainframe. Now, to clarify something up front, file systems, as we know them today, aren't really considered databases, technically speaking. So when you think about, hey, I've got folders on my Windows server or my file server, you think of those as file systems. Technically speaking, but in the early days of computers, users weren't storing documents or word processing documents or images. These things just simply didn't exist, on the storage on the disk of your mini computers or mainframes. So all data was really being processed by a custom program that you wrote or a third-party program that you bought. So file systems were really where the data lived. So you can think of things like an insurance record or customer records or invoice records might actually be a file with some kind of index on it. So we consider file systems one of the four basic types of data storage models. So first up, index file systems. At the most basic level, you'd have a flat file. Very uncommon in those days for it to be a comma separated values, but you can think of it as the equivalent. In those days, they were more commonly fixed width formats. So each section, each row had a fixed number of bytes or fixed number of positions for a certain field. So last name might be 10 characters, first name might be 10 characters, street address might be 20 characters, but you reserve the whole character list as opposed to inserting commas. And these file systems weren't really databases at all. They were just raw files, a customer file, an address file, an invoice file, a header file, each of them a separate physical file for the most part. They weren't always a separate physical file depending on the operating system, but close enough. And your application, written in COBOL, Fortran, C, would read or write those files directly. It was simple and it worked, but it didn't really scale well. There weren't a lot of rules about how those files interacted. Any program with the right permissions and knowledge of the file format could read or write them directly. So, things like locking one program, locking a record, preventing another program from reading or writing that record was pretty primitive in the early going, right? Enter the hierarchical database. So not just reading or writing a file that got created, but talking to something else that physically talked to files. And the first of those were hierarchical database. These systems allow you to store multiple record types in a structured tree-like format. For example, you could store invoice headers and invoice line items together, nested in a single data structure. The most famous of these systems, still around today, was IMS, developed by IBM for the Apollo space program, boys and girls. Yes, IMS was invented before we landed on the moon. And believe it or not, IMS became a dominant solution for storing business and enterprise data. This was a big shift because your software application wasn't accessing the file directly anymore, but instead it talked to a database management system or a series of libraries or functions like IMS, which handle the interaction with the actual files behind the scenes. So this pulled you away from some of the complexity of the structure of those files. It was still pretty complex, but behind the scenes, it could handle more things like record locking and reallocating space, doing things that you didn't have to do in your program that IMS handled for you automatically. These hierarchical databases were great, but they had limitations, especially as data models became more complex. They were rigid, and that's where the network data model came in. So as computer systems evolved, standards bodies began to appear. One of the first was a group called the Conference on Data Systems Languages, or CODISL. One of the first standards that they came up with or designed was a CODISL database or a network database. Network databases allowed you to have pointers or connections between record types in the same physical database, if you will. So you could have an employee in a department, two different data structures, where in a hierarchical system, they would be nested. A department would live on top, employees within that department. In a network data model, you could have a direct pointer from an employee record to a department record. So you could effectively navigate the tree, even though they were stored separately. This made complex relationships easier to manage than in a hierarchical structure. One of the big players in the space was Cullinet out of Boston. They produced a product called IDMS, which became a standard for network databases on mainframe systems. DEC had their own version called DBMS 32, which served the same purpose for back VMS systems as IDMS did for mainframes. These network databases were more flexible, but also more complex to implement. But they definitely opened the door for more sophisticated data modeling and enterprise applications. Now, finally, just as we're wrapping up the 1970s, and we're going to talk a little bit more about this in a subsequent slide, as the 70s ended and we headed into the 80s, relational databases began to take hold. Today, this is the model most of us are familiar with. It dominates modern systems. Relational databases store data in tables, and they use structured query language, or SQL, for querying. They're highly scalable at this point. They're highly flexible, and they relieve a lot of the complexity for navigating against data. The first major players in this space were, System R, which was IBM's original model, because they invented the relational model itself. We'll talk about that in a minute. But Oracle was one of the first commercial vendors, as was Ingres out of the University of California at Berkeley. So to sum it up, we started with flat files that could have indexes for speeding up finding an individual record, but a lot of times these were handled just sequentially, first in, first out. We graduated to hierarchical databases and network databases, and eventually we landed on the relational model, which still powers many of the world's applications today. I might even say most of them. We'll talk in subsequent lectures about NoSQL, non-relational databases, or post-relational databases, but the market is absolutely dominated by relational databases today. In terms of brands, we can talk about some real-world examples of the database and file systems that were there in the 70s and 80s. Almost every major hardware vendor had their own take on how data should be stored and accessed, their own hierarchical database, their own network database, their own index files. While the concepts were similar, the implementations were wildly different. So if we start with the big players, IBM had vSAM, virtual storage access method. It's a high performance file system. Not quite a database, but widely used in mainframe environments. So you're processing the phone bills for the telephone company every month, insurance records. Many times, the data was stored in vSAM files. But IBM also developed IMS, or Information Management System. Again, as part of they did it to deliver on the Apollo program for NASA. This was one of the first large-scale hierarchical databases. IMS was a big deal, and it's still a big deal. It's still used in any number of legacy applications when you have to process massive volumes of data very quickly. Things like credit card statements, phone bills. That's a classic use case for IMS. DEC, which we've talked about before, offered a file system called RMS, or Record Management Services. Like vSAM, it was more of a file handling tool than a full database. Now, you could store things in folders and directories, much like a real file system on DEC. But if you were reading and writing, business records, you would have stored those records in RMS, which provided a variety of different index types and storage types. But that was the file system you would use. DEC also built their own network or codicil database called DBMS 32. Based on the codicil model, it's their answer to Cullinet's IDMS. Speaking of IDMS, it was a network-style codicil database developed by Cullinet, widely used on IBM mainframes. But it wasn't just IBM. Other vendors jumped into this game too. So as you're starting to see the tail end of the 70s, the birth of the third-party software developers. So Cullinet wasn't a hardware vendor; they were purely a software vendor making a database product that ran on IBM. Almost every smaller vendor, so Prime Computer, based in Massachusetts, long gone, they had their own hierarchical database called Prime DBMS. HP had their own codicil database called Image 3000. Burroughs, which was a competing competing mainframe vendor, they had DMS. Siemens Nixdorf had DMS, and then last but not least here on this page, McCormick and Dodge. So they were one of the first vendors that wasn't a hardware company that offered a software product, a database product called Infos 2, which was a codicil database system that worked across platforms. So while Cullinet's IDMS was primarily a mainframe only product, McCormick and Dodge literally ported their software to run on a variety of machines, including a number of the mid-range vendors like DG and Hewlett Packard and DEC. Because every major computer manufacturer had their own file system, their own hierarchical database or network database, while the concepts were same, the details were very different. And because of that, portability was a nightmare. If you wrote an application for one vendor's system, it typically wouldn't run on another. And even the database interface, the way you connected to the database and queried it, the function calls used to read and write records was very vendor specific. So once you picked the platform, you were pretty much locked in. You were locked into that vendor's hardware, that vendor's operating system, and that vendor's database. So you were basically, if you built a product, you were building it around that ecosystem. But change was coming. So by the late 1970s, we began to see the first commercial implementations of relational databases. So the relational databases were one of the first products that ran on multiple vendors' hardware and also abstracted you from some of the complexities of interacting with that data through the use of the SQL language. This was a huge turning point in the computing industry. It started with IBM's System R product, which was based on the ideas of Dr. Ted Codd, who invented the relational model itself. System R was the first, coded version of the relational database based on Codd's paper, and it laid the groundwork for what you now know as IBM's DB2 product. Around the same time, over at UC Berkeley, a small group led by Michael Stonebreaker, who I worked for at Ingress, developed a system called Ingress. That project was built on BSD's version of Unix, and like many systems of the era, also ran on VAXs under VAX VMS. Ingress would go on to influence a number of commercial and open source databases, including a successor database to it known as Postgres, is one of the most popular relational databases that you're using today. And then, of course, there's Oracle. Everyone knows the name today, but the very first commercial release of Oracle's relational database came out in about 1979, and that was a major milestone. They were one of the first to really capitalize on the relational model commercially, and were one of the first vendors that saw value in porting or making a version of their product available for lots of different hardware platforms and lots of different operating systems. Part of this change was the critical element of what programming language you used to work with on the various machines in the 70s and 80s. There wasn't a lot of commercial software available, so the programming language was the primary way that software developers wrote custom functions or custom processing against a particular database, a particular hardware platform, a particular operating system. Historically, you can think of three types of programming language. So machine language, assembly language, and what we now call third generation languages or 3GLs. There's also 4GLs and 5GLs. We'll talk about that in subsequent sessions, but for the purposes of today's conversation, we'll just consider these three. They all represent different levels of abstraction from the hardware, and each has its own sort of key purpose, strengths, and trade-offs. Machine language is as close to the metal as you're going to get. If you start at the lowest level of machine language, this is the native language of the CPU, a stream of binary code made up of ones and zeros. Each instruction corresponds directly to a CPU operation, things like loading data into a register, jumping to another memory address, or performing arithmetic operations. It's very hardware specific. There is very little abstraction. It's extremely fast and extremely efficient, but it can be very difficult to read, write, or debug. In terms of use case, much rarer to be coding in machine language today, but still widely used in embedded systems for performance tuning at the very lowest level. Now, one step above that, enter assembly language. Assembly is still pretty low level. It's a symbolic representation of machine code. So instead of ones and zeros, you're writing mnemonics like move, add, jump, sub. Each line of assembly maps closely, often one-to-one to a machine instruction, but it's easier to read. You still have to manage registers, memory addresses, and all the hardware details directly, but it's much easier to write and much easier to understand than raw binary. Still hardware specific. Each CPU family has its own assembly language, but it does offer full control over the hardware while requiring deep technical knowledge of the chipset you're working with. Very fast, but it's a little harder to maintain than in some cases much harder to maintain than typical 3GLs, but certainly easier to maintain than machine language. Use case, systems programming, bootloaders, file system drivers, anything performance critical would often be written in assembly and is still written in assembly. Now, last but not least on our list are 3GLs, or third generation languages. And you can consider these the human readable abstraction of programming. These are what most people, 3GLs are what most people think of today as normal programming languages. So, common examples: COBOL, Fortran, C, BASIC, Java, Pascal, you name it. These languages are designed to perform and be platform independent, easy to read, more expressive. You don't necessarily need to think in terms of memory addresses or registers, but in certain of these, you have access to a lot of low-level structures like you would have with assembly at a different level, but similar concept. But really, you're thinking more in terms of logic, control structures, functions, and data types than the low-level workings of the machine. Third generation languages are compiled and linked into machine code that is actually native to the operating system. If you're using a modern language like Java or C#, those are not compiled into machine language, but into kind of a bytecode that's run by a piece of software that is translating that into machine code. Again, faster to develop, gets you abstracted away from the operating system. Use case of 3GLs of everything from enterprise applications and web development to scientific computing and mobile applications. In short, you can think of these three as a spectrum of abstraction and control. Machine language gives you maximum control with maximum complexity. Assembly gives you slightly more human readable ways to work with the hardware, and a little bit easier to maintain. And 3GLs let you write software that's much more manageable and scalable to maintain, especially for large teams and for long-term maintenance, but doesn't give you the fine-grained control that you might need to really drive the power of the hardware that you're working with. When we think of programming languages today, we often assume that there was a pretty big degree of portability. That if I write in Java, I can write in Java on almost any operating system. Back in the 70s, 80s, this wasn't true. So each hardware platform and operating system typically had its own favorite or supported languages, which often had their own quirks associated with them. So if we start with IBM for a second, first of all, their mainframe, quote unquote, didn't run just one operating system. They had several: OS 360, MVS, VMCMS, just to name a few. And their mid-range systems like the System 34, the System 36, the System 38, all of which eventually evolved into what we now know as the AS400. Again, they ran slightly different operating systems. On these platforms, the dominant languages tended to be COBOL, RPG, PL1, Rex, later JCL, Fortran. Each of these languages really had a different use case. So, business logic, scientific computing, system scripting, they all had sort of specialties. And of course, in the 70s and 80s, assembly languages were widely used, especially when developers need to get close to the metal. For the mini computer vendors, take DEC, for example, again, they had multiple lines of hardware and operating systems as well. PDP-11s running Ristus, DEC 10, DEC 20s running TOPS 10, TOPS 20, VAXs running VMS. Each of these were unique operating systems, and they supported a variety of different languages. DEC had Macro 11 or VAX assembly for assembly language development. They made a stab at producing a easier version of assembly to work with called Bliss 32, which was based on the Bliss language developed out of Carnegie Mellon, which stood for Basic Language for Implementation of System Software as opposed to application software, stuff that ran the operating system as opposed to business logic. And then other high-level options that ran on DEC equipment: Basic, COBOL, C, Fortran. If you were building, kernels or device drivers or compilers or systems libraries on a VAX, you'd be using Bliss 32, alongside probably some VAX assembly. But if you're running, business logic or business programs, you'd be coding at a higher level in COBOL or Fortran. Vendors that were running primarily the Unix operating system regardless of whether or irregardless of which camp they were in, the System 5 camp or the BSD camp, they were mostly using C as the programming language. There were ports of other languages to Unix boxes, but C really kind of dominated as the language. And then most of the other vendors offered their own custom languages as well. So if you notice, Tandem had their Guardian OS. They had a version of COBOL, but they also supported their own language called TAL. Wang Laboratories, had support for BASIC, but they also had their own macro language called WPS Macro, and they had their own programming language that was built into the operating system called PACE. So there were a few programming languages that ran across a number of different vendors, even though they weren't the same version of the language. But in often case, the operating system hardware developer developed their own custom languages for those platforms as well. Now, it's just one example. Let's just talk about COBOL because it was so widely used. The Codicil Committee attempted to begin to standardize languages, certainly the popular languages, and ones that ran on multiple operating systems. And the first one they tackled was COBOL. COBOL, which stands for Common Business-Oriented Language, has been around since 1959. That's right. It predates Unix, C. It even predates moon landings. Over the years, it's gone through lots of standardization phases. Each one adding features, improving the way it worked, or trying to bring COBOL up to date with contemporary programming needs. COBOL 60, which was the first COBOL, that original standard was the first one developed by Codicil around programming languages, but it still wasn't much of a standard. The COBOL compilers, the COBOL language on each operating system was quite different. COBOL 68, named for the year 1968, was really the first standard. This was the first official standard that was designed by Codicil and released by ANSI. Released in 68. It brought a lot of consistency to the language across vendors. So COBOL 68 basically codified what people were doing in practice, and it set the stage for greater portability. So if you were using a COBOL 68 compiler, you were using it on DEC, you were using it on IBM, it worked basically the same way. The commands, the syntax was the same. What wasn't the same was all of the third-party operating system functions. So making calls out to IBM's IMS or vSAM would be vastly different in COBOL on a mainframe than it would be COBOL on a DEC system. So while the standards committee helped to standardize the syntax, it didn't mean that code that you wrote for one platform would easily run on another platform. Later versions of COBOL added logic like things like if then else or perform until. Today you see operating system languages have a lot of functions right out of the box. Way back when, features started to be added slowly over time. The first major overhaul, and when I started dealing with COBOL, was in 1985. It was a major reconstruction of the language, adding more scope terminators, making file I/O improvements, adding more support for complex data structures. But they didn't stop there. 2002 was the first version of COBOL that supported object-oriented features like classes and objects, which would make it more compatible or more palatable to developers who were used to using things like C++, which was object-oriented from the get-go. And then, even today, COBOL 2014 is the last major enhancement or standard enhancement to COBOL. Again, modernizing COBOL while trying to keep it compatible with the mountain of legacy code that you might be using on older platforms. So the more popular a language got, the more likely it was that a standards body would come along to try and standardize it across different vendors. Certainly true of COBOL, certainly true of Fortran. So we often think that we're living the era of the proliferation of programming language, but the 1970s saw a rich diversity of programming languages as well. Some new, some that were maturing, many were highly specialized for a particular hardware vendor or operating system. It was a pivotal decade in the move from procedural programming to structured, modular, and object-oriented paradigms, and it laid the foundation for modern software development. Now, just to give you a sense of the variety of programming languages out there in the 70s, I just put together a short list, well, not that short, of 20 plus popular programming languages. Some of these you'll absolutely recognize, such as BASIC, Fortran, COBOL, and C. These were the big names, but there were plenty of other languages that you may never have heard of, and that some of them are still around. Some of them died with the hardware vendors that supported them. One popular one was Smalltalk, introduced in 1976. It was one of the first truly object-oriented programming language, and it really helped how we shape object-oriented programming even today, how we think about objects, how we think about messages between systems and reusable code. There's Ada, which was a standard the U.S. Federal government backed by the mid-'80s. If you sold software to the federal government, it needed to support Ada, either be written in Ada or support an interface that was callable from Ada. And that was the government's effort to get some standardization across the different parts of the government. So the point of all this is, there were many, many programming languages being invented, explored, and used across all sorts of industries. Now, to be fair, we probably have even more programming languages today with specialized toolkits and frameworks, for web, mobile, data science, etc. But it's a mistake to think that the 70s and 80s were just COBOL, C, and Fortran. The era was a hotbed of innovation with language design exploding as people tried to figure out what was the best way to build complex systems. So as we get close to the end for part one, we're going to wrap up part one by talking about a final category in our historical overview, application software. Now, when we think of modern application software, like a CRM system or ERP product or supply chain management or something as simple as a general ledger, we think of them as polished third-party products you just buy off the shelf. But in the early days, that's not actually how it worked. Prior to the 80s, most business software was developed in-house. Companies wrote their own custom programs, typically in COBOL, RPG, PL1, Fortran, and these programs were tailored to the unique business processes of that business. Now, why was that the case? Well, there are a couple of big reasons. First, the hardware and operating systems were all over the place in terms of standardization. So you had different flavors of mainframes and mini computers, and each one ran its own proprietary operating system. So for a third-party vendor to write software for a platform, say an IBM mainframe, meant that they were mostly locked into that platform. So, that software couldn't easily be ported or wouldn't easily run on a DECVAX or an AT&T 3B2. Portability was almost non-existent. So you picked a hardware vendor, you picked an operating system, and you wrote code for only that platform. As a result, software vendors had to pick a platform and stick with it. And most companies believed that their internal processes at that point were so unique that off-the-shelf solutions, which were fairly simplified, just wouldn't work. They saw their business logic as a competitive advantage, and the only way to properly capture that was to build software themselves. Now, things started to change in 1969 when IBM unbundled software from its hardware. Part of a consent decree that IBM signed with the government in the 50s required them to unbundle. So prior to that point, when you bought a quote-unquote system from IBM, you bought everything from them. The terminals, the hardware, the disks, the memory, the software, everything. It was a one-stop shop. Because they had such a dominant position in the marketplace, the government considered them a bit of a monopoly, and they negotiated with IBM to begin unbundling, like allowing customers to buy pieces from IBM and pieces from other vendors. That was mostly hardware in the 50s and early 60s, but things started to change in 1969 when IBM unbundled software from hardware. Before 1969, if you bought an IBM mainframe, much of the software you needed came included. The compilers, the business applications, everything. But following this antitrust pressure from the US government, IBM began to unbundle the software, which opened the door for third-party developers to begin entering the market. Because as a small software vendor, you didn't really want to compete with IBM. And this really was a game changer. Although early independent software vendors emerged in the late 70s, it took time for their products to mature because it took them time to actually build these products. And in most cases, several years to get a fully functioning version of the system out the door. But by the mid-'80s, third-party business software really started to take off. Now, why did third-party software start winning? Well, there were several factors that drove the shift from homegrown to package. First off, we talked about IBM's unbundling. This made the third-party software market viable. You could write a product for the IBM mainframe, and you weren't necessarily competing with IBM to sell that product to your customer. The rise of mini computers like the HP 3000, DECVAX, encouraged modular open systems, encouraged vendors to consider building a software product that would run on multiple hardware platforms. As these third-party packages started to get traction, they ended up being cheaper to buy versus building yourself. Oftentimes they were faster, and they started to get easier than building custom solutions from scratch. So business functions, particularly standardized functions like general ledger, payroll, HR, they just were not unique enough for a particular business to justify a company writing their own custom code. So they began looking to buy commercial products that would run on their platform. So rather than building everything in the house, these businesses started to buy off-the-shelf packages for standard functions and focus their internal development only on areas where they had unique needs. Now, there were a number of popular vendors that started producing commercial software products across operating systems in the 70s and 80s. I've taken a little bit of just a random sample here for you to get a flavor for it. Some of it, these names you're still going to actually recognize. So at the top of this list, we've got the SAS Institute based out of Cary, North Carolina. And they built statistical analysis software. They supported IBM, DEX, CDC, many other platforms. So they were one of the first truly vendor or platform independent software platform, and still around today. There was a company called National CSS. They offered a product called Natural, which was essentially a report writer. They called it a fourth generation language, but it was a report writer that ran on IBM mainframes. Information Builders out of New York, they made a product called Focus. Again, the Focus report writer could run on top of a variety of different data sources and file systems. VSAM files, DEC RMS files, hierarchical databases, Colonet databases. And Focus was a great product as a replacement for building custom COBOL programs for writing reports against your data that lived in these file systems. CompShare was one of the first companies to produce what we would consider a finished application platform. The SAS Institute Statistical Analysis, Information Builders, and National were report writers, but CompShare produced a full financial planning application for the IBM mainframe. MSA, or Management Science of America, they delivered one of the first commercial financial suites that included GL, payroll, and HR, and they supported both IBM and DEC platforms. McCormick and Dodge, extremely popular in the 80s. They offered both a database product, which we talked about, Infos 2, but also an accounting package that ran on DEC VAX and IBM mainframes. Ask Computer Systems, one of the earliest successful ERP vendors. Their MRP systems ran on mini computers like the HP 3000 and the DEC VAX, and even Prime machines. And yes, at the bottom of our list, last but certainly not least, SAP got their start here as well. So SAP's R1, the first version of their ERP product, which we now know as SAP ERP, that actually ran on the IBM mainframe. So by the mid-'80s, packaged software was gaining ground fast, especially in small to mid-sized businesses where developed resources or software developers were a more limited resource. The rise of third-party vendors, particularly on mini-computer platforms, gave companies access to scalable, reliable software without the need for massive internal development teams. And it all started with a combination of hardware evolution, vendor openness, and a critical regulatory push that unbundled software from hardware. So, where were we in the middle of the 1980s? In summary, circa 1985, we were probably at the high watermark for the number of different hardware vendors and competing proprietary operating systems in the computing world. It was a crowded, fragmented landscape, and everyone had their own flavor of tech. Prices for hardware continued to come down, and the number of vendors entering the market, both as hardware vendors and software vendors, was increasing. In terms of data storage, file systems, along with hierarchical and codicil network databases were still the dominant models. Most data was stored in things like VSAM files or IMS, some codicil network models. Very little was in relational at this point. I'll just remind you, file systems, more technically a database, but for a lot of use cases, it was back then and functionally close enough. Remember, this is pre-Windows, and almost all data lived in structured files that were read or written by third-generation programs, with the exception of documents like a word processing document, which weren't like the word processing documents you use today. They were not a what you see is what you get. You were often typing text and formatting commands right into the document itself. And until products like Wang word processing system came along, or DEX WIPS Plus all-in-one, you didn't really have the concept of a document. That being said, commercial relational databases were starting to gain traction. By 85, companies were beginning to use relational systems for more than just side projects. They were starting to store core transactional workloads in these systems, particularly on mini computer platforms. Sometimes they were just offloading data processing from an expensive mainframe into relational databases on a cheaper mini computer for reporting analysis. Other times developers were, deciding to use relational files instead of a flat file, accessing their COBOL program. So let's make it talk to a relational database instead of a flat file, particularly on mini computers. By this point, the big three programming languages that would work across platforms were COBOL, Fortran, and C. COBOL was dominant in the business world. Fortran was more common for scientific and engineering circles. C was rising fast. It was the de facto standard on Unix environments, although it wasn't yet the go-to language for more of the proprietary systems. Still, if you wanted portability, those languages were probably your safest bets. Users primarily interacted with computers via CRT terminals. At this point, teletype terminals were starting to go away. Almost everybody had a CRT. So when someone said they were getting on the computer, what they really meant was that they were powering on their terminal, logging into a mainframe or mini computer, and working through a text-based interface. I mean, this is pretty much the standard. Even though hardware prices had started to come down, CPUs were getting faster, memory and disk were getting higher capacities and cheaper prices, they were all still pretty expensive, especially when measured per unit. That meant programmers still had to be highly efficient. They spent a lot of time writing code that was lean and carefully optimizing programs to fit within the system resources they had. Efficiency wasn't just a nice to have, it was absolutely necessary at this juncture. So what's next? That's where we stood by the 80s, but then something big happened. The personal computer was invented, and local internet and networks began to proliferate. Now, at first, these seemed like small things, kind of niche, kind of scrappy, but they ended up driving a fundamental shift in computing architectures. They didn't just complement these big machines. Ultimately, they started to compete with them and make heavy inroads into the architecture of modern systems. So in part two, we're going to take a look at this PC revolution that reshaped the world of enterprise computing and set the stage for everything else that came next. And with that, we will see you in the next episode. Ciao for now.